Hello, my name is Prem Malhotra, and along with Sujit Joseph, we will be sharing the journey at Cisco for transformation of search. Before we begin, a bit about ourselves. I am Director of Enterprise AI, leading a team of engineers in search and AI. Our focus is on information findability for both technical and non-technical information for our customers, partners, and employees. So besides doing innovations in search such that search is a delight, we are also digitizing business. One example is case deflection for customers.
And I'm Sujit Joseph. I'm a senior enterprise search and cloud architect with over 16 years of enterprise search experience.
We will talk about the transformation we have done for the most used application on Cisco.com. It is a search capability used by customers, partners for finding information about our products and solutions. 4 key aspects of transformation were to combine Elastic with AI, use open source, use modern cloud design, and global cloud deployment. This resulted in 3 dominant user experience benefits. First one, the guided information exploration using smart typeaheads. Second, information on fingertip, so that it reduced the need to read long documents and find the needed information. And third, the performance, especially in the APJC. There was over 50% or better performance improvement. Now let's look at the demo of this system. But before the demo, here's the strategy or the approach used. That idea being that if you pick a book from a library and you open the book to the right page, that is the approach that we are using to get an answer on the fingertip. So what you see here is 2 panes in the browser. The left one is the new search, and the right one is the old one that is used for comparison. So I'll just do one example of a scenario where customer is looking for information and what happens. So it turns out that CAD 9600 is a popular product, and customer wants to know the line card capacity for a chassis. Now you notice as I started typing, the typeaheads that came in here changed, and turns out that one of those typeaheads already exists, so you can click on this. If not on this, you can keep on typing and you can submit the query. Either way, search happens. So you click on this typeahead, you get this box. This is the Deep QA capability, which gives you an answer right at the first paragraph. It supports 4 line cards, and then it gives you an additional inspection, how to configure these cards and so on. Let's try the same search on the old search engine that we had. So we copy paste, so user will never type so much, but let's see what happens. So what you get is a series of URLs, books, and data sheets that you have to go struggle with it to find the answer that you're looking for. So let's go back to the presentation. So I'll talk about 4 elements into the design of the Deep QA, how the documents are processed or chunked, then typeaheads are generated from these documents using AI, and then the query or the typeaheads are matched to the answer, and then everything got deployed in production. So document types that we were addressing were these different kinds, which are ranging from data sheets to the configuration guides and so on about our products, about 350,000 documents. Now, here's some examples. The 2 different kinds, they look very different. Now, what did we do? So we used the characteristic of the documents that they are hierarchically heading organized, so that we can leverage that to parse the documents in a way that parsers can address different kinds of documents as well as generate these documentaries. And this documentary, what you see here, is one example, and then the example highlighted is a chunk that has been picked from this documentary about the IP fabric for a media solution, and that is what you see on the right hand side. If you search for a media solution for Cisco Nexus 9000, this is what shows up, and this is a way to kind of chunk the document in multiple units. So 350,000 documents led to about 3.5 million chunks. Now the generation of type heads was done. Type heads look at each chunk and they break it down further and look for pieces, few sentences which have the good information quality. Then a hint is generated for that using the NER process or the entity recognition process. And this is fed to this model called sequence-to-sequence transformer, which comes from Microsoft. And it produces an abstractive language generation output, which is a questions. So typically one question per hint is generated, and then one chunk will have multiple of these sections or group of sentences to generate question for. There's a limit of 464 tokens per input to the sequence-to-sequence transformer. Finally, the questions are sorted or further reduced in number because some of the rougher or not so good questions are weeded out using rule-based approach. And finally, the questions are again lexically reordered by some scoring that we did on the quality of the questions. So overall, from 3.5 million chunks to 8 million initial question set, then 1 million after initial sorting and throwing out not so good questions, then finally it says 360K that we were using. Now, what did we use for the quality check? So this is work we took from linguistic area, that there are measures called TTR, token term ratio, and MLTD. These are different ways to look at the content and come up with scores. We combined the two scores together in a way using empirical mechanism that we found a scoring that actually worked for the content that we had and the questions that were being generated. Now finally putting it all together to get the answer chunks. So this shows what happens. Customer query comes, its query processing happens, and then there's a deep CT box here that actually assigns weights to the terms in the query. This is using an AI model. And then elastic retrieval happens. Now if it's a type head, it retrieves directly from the chunk that was generating the type head. And finally, there's this squad model, which looks at the chunk that was retrieved and tries to find further a line in it or sentence in it that could be a closest answer to the query, like the example that you see. If somebody was looking for HSRP question, it gave you an answer right on the spot on the title of the box. So there are multiple models used for different intents. Now, squad model is one that is based on BERT. All these are based on BERT, but there are different trainings done to the BERT models to generate the needed outcome. So now this is a more expanded version of that flowchart of what happens when a chunk is retrieved, and the real product has a higher, more complex way to outline it. And in this case, the product is identified and the query is made with the product and the user input. And for type head, no query is needed. You just go to the chunks that generate the type head. Now, making it all production ready involves making sure these models actually run in a good time, typically less than 20 milliseconds per query. And that's required some of them available off the shelf that we can use. Rest had to be fine-tuned to make it run faster. And all this runs on NVIDIA server card Tritron on T4 GPUs in the Google Cloud Platform. Now there are slides in the deck which explain all these models in detail that you can look at. So what are the highlights of this work? AI can be effectively integrated with search, though for its rough edges you have to put in some procedural rule-based features so that it can all be made into a solution. And a content analysis is a key to visualize a solution. So next I will ask Sujit to show us a journey to GCP. Thank you.
Thank you, Frank. And I will be talking about how we build a scalable enterprise search platform in the cloud in GCP, and how we migrated Cisco.com search to this platform in a span of around 6 to 8 months with a team of size 12. I've had the opportunity to work on enterprise search engines since the early 2000s. I worked on BERT SQUAD, Autonomy, Idle, FastDSP, a TBO, etc. And you'll see that all of them share the same anatomy. And here is an anatomy of an enterprise's platform. At the top layer, you see data sources, and you have connectors or crawlers which would fetch the content from the data sources. The fetched content then goes through a document processing workflow, which would do enrich of the metadata and the content, etc. And then it gets tokenized and indexed into a search engine. On the search layer, you see an UI, an API, search API layer, and then the query goes through a query processing workflow and finally hits the search engine. You'll also see search administration UIs, you'll see query analytics, reporting UI, etc., relevancy tuning tools, etc. So when we build the enterprise's platform, we actually build it using the same anatomy. For example, for the data layer, we have Cisco.com site content, and we use Adobe Experience Manager as a CMS, as a content management system. We have content in databases. We have lots of Cisco websites. We have video and community content, etc. So as and when a Cisco document is published in the Cisco.com site, we actually now push the document to Enterprise's platform for indexing. For the rest of the data sources, we have built connectors based on Apache Spark. We have connectors for database, Snowflake. We have a crawler. We also have API connectors. For the crawler, we use an open source crawler known as Sparkler. We actually evaluated multiple crawlers like Nudge, Heritrix, and we found Sparkler to be the most performing. We run the Sparkler as a Dataproc job in GCP, and an on-prem, we run it as a Spark job deployed using a Spark operator on a Kubernetes cluster. And for the Kubernetes cluster, we actually use a custom gang scheduler known as Volcano. For the crawler, we actually use Cloud SQL to store the checkpoints and for storing the crawl meta store data. The crawl documents are uploaded into Google Cloud Storage, and the crawl document reference and the metadata is sent to a messaging service known as Google PubSub. And we do have end-to-end traceability of a document that is fetched from a connector or a crawler all the way to the search index in Elastic. And these are sent as events from the connector to the variety of subsystems that we have. These events are sent to PubSub, and ultimately it's stored in Elastic and BigQuery. Any errors during the crawl is stored in Bigtable. Sparkler was missing a lot of basic features that are needed for a crawler, and we did add those features, namely incremental crawling, form-based authentication, JavaScript crawling, duplicate content detection, etc. As to the site search, that is Cisco.com, as I mentioned earlier, we use AEM, and we built a component in AEM which would detect new page activations. And the document that is published is uploaded to GCS. And the GCS URL and the AEM metadata is then sent to PubSub to be finally sent to the next subsystem, that is the document processing system. So we use Google Dataflow for document processing workflow. It is essentially a managed data processing service which supports both streaming and batch mode, as well as it supports Apache Beam SDK. During this workflow, we have multiple processors which would enrich the content based on business logic. We do text extraction using Tika here. We also apply a lot of relevancy signals which are stored in Cloud SQL. For locale detection, we invoke a microservice from Dataflow. And even within the document processing pipeline, we have end-to-end traceability across each processes and microservices. All the errors and audit and metadata data goes to Bigtable. The final process document is stored in GCS, and GCS reference of the process documents is sent to PubSub for the next system, that is the AML processing. We also do have auto-scaling enabled in the data flow. So as and when the load increases, you will see that the data flow worker nodes this increase. For AML processing, we actually chunk the documents into passages. And these passages are sent to PubSub. And these passages goes through multiple AML microservices to perform things like generation of typeaheads, along with filtering, as I mentioned earlier. We stored the passages and the mapping between the document ID and the chunk ID in Firestore. The passages are then sent to Logstash to be indexed into Elastic. We have HPA, that is horizontal autopart scaler, enabled for the AML microservices as well. So the output of the document processing workflow, as well as the AML workflow, is sent to PubSub, and we have Logstash microservices deployed in GKE, Google Kubernetes Engine, which would actually download the passage or download the document from GCS, and it would be sent to Elastic for indexing. We do have separate clusters and indices for, say, autosuggestions and passages, and a separate one for documents. We also use Logstash to apply partial updates, especially relevancy signals on Elastic documents. We also use Logstash to read from Elastic and send audit events to PubSub. The Elastic credentials are mounted from Kubernetes secrets, which are synced with Google Secret Manager. And we also have autoscaling enabled on Logstash microservices. The search engine that we use is Elasticsearch and is deployed using ECK operator, that is Elastic Cloud on Kubernetes operator. We have multiple Elasticsearch clusters that is deployed across 2 regional GKE, that is Google Kubernetes Engine clusters, deployed across 2 GCP regions, one in US and one in Asia. The data nodes are distributed across 2 zones per region, and the master nodes are distributed across 3 zones. We do have autoscale enabled on the Elastic node pools. The Elastic nodes are deployed as stateful sets via ECK operator, and we've been running this in production for the past 8 months, and I can say that it's very highly stable. For index storage, we use persistent volumes, and for we use GCS for storing the daily Elastic snapshots. The indices are 100% memory map for performance. So without a memory map, the searches can be slow, as the indices will be read from persistent volume, which is the slowest. So we had looked at an option of using local SSDs, but then it adds in a huge amount of operational overhead. For example, Elastic upgrades and automated GKE upgrades are not easy, and automated GKE upgrades are not even possible if you use a local attached storage. So to ensure that a search is performing fast, we have to ensure that all the indices are in fact memory mapped. We use Kubernetes node affinity and zone-based Elasticsearch shard allocation awareness to ensure a proper distribution of these nodes across the zones, as well as the shards across these Elasticsearch nodes. For the data nodes, we use N2 machine types, which has a high clock speed, so we do get a slightly better performance in terms of Elasticsearch response time. For the master nodes, we use E2 machine types. We have different node pools configured for master nodes and data nodes, and we use Kubernetes tains and tolerations for scheduling the pods into the appropriate node pools. We use one Elasticsearch node per GKE node. And in our dev environment, during a GKE upgrade, we found that when we had multiple Elasticsearch nodes deployed under a larger GKE node, like say 64 by 416, it cost a 3-minute outage during the upgrade. For the synonyms, we use a Google file store that is mounted on all the Elasticsearch pods. And the reason we couldn't use the config map was because of the 1 MB size limit. So we have a custom synonym loader microservices, which would download our synonym dictionary from GCS and download it to the file store, and then it invokes the reload search analyzer API so that the Elastic nodes pick up the latest dictionaries. We measure Cisco outcome search relevancy using relevancy performance indicator tool, which essentially measures relevancy using a DCG algorithm. It is running as a Spark job. For load testing Elasticsearch, we use JMeter operator, essentially JMeter running as a microservice within our cluster. So for the search UI and AI query processing, we use microservices, deployed in a service mesh that is Istio, set up in a multi-cluster replicated control plane setup. It actually connects the two search GKE clusters that we have deployed across US and Asia. It enables cross-region failover services as well. So the search.syscard domain name for the search UI is mapped to the GCP HTTPS global load balancer, which has the network endpoint groups as a backend, and these negs talks to the Istio Ingress gateway parts that is deployed in each zone in each of the two regions. The backends are protected by GCP Cloud Armor to protect against bot attacks. We have Istio virtual services, which will route the traffic across the search and the AI microservices and Elasticsearch. A single query passes through 13 microservices to perform a search. We have a deep QA system which enables Passage Q&A search, and it uses a couple of AI services. There is DeepCP, which essentially uses BERT attention weights to influence the term pools. We have query intent detection, NER. We use BERT SQUAD for answer detection. Depending on the type of the query, based on the query intent, we use multiple search templates. We have horizontal pod autoscaler enabled for the microservices. And the GKE node pools have autoscaling enabled. We use E2 machine types for search and AML GKE node pools. For AML services, we use T4 GPUs with NVIDIA Triton Inference Server. Essentially, it gives us the capability to load multiple AML models with a single GPU. And we use Kubernetes taints and tolerations for pod scheduling to the corresponding GKE node pools. The Elasticsearch credentials are stored in Secret Manager, and the search API syncs up with the Secret Manager to load up those credentials. And it also performs the duty of routing the request to the various Elasticsearch clusters that we have based on an API key. The Elasticsearch query performance metrics, the actual query in the API key, is sent real time to PubSub and is stored in BigQuery for query analytics purposes. We use Grafana and Kiali for visualizing the Istio metrics. We have configured timeouts and retries in Istio. At the load balancer level, we have configured rate throttling and HTTP3 support for better performance. We also have rate throttling at the Masher API level. We've seen a performance improvement of 50 to 73% with a region 2 that is Asia. So this is how all these components fit together. Here I'm portraying the key components of the enterprise's platform. You can see the on-prem connectors and the data sources, and the connectors in GCP that are based on Google Dataproc, the document processing pipeline based on Dataflow and the AML microservices, and the documents are indexed via Logstash services deployed in each of the two GCP regions, and it in turn passes the document to Elastic for indexing in each of the index regions, and we have a load balancer to route the traffic across the regions with an anycast IP. This portrays all the components that we talked about in this session. On the right-hand side, you see the query components, the GKE clusters. On the left-hand side, you see the ingestion-related components. This talks about the on-premise Kubernetes cluster and the data sources. We have Jenkins and Spinnaker as a CI/CD platform, along with observability. When we talk about the journey to cloud-native search, we had key focus areas. We use a modern architecture to build this platform. We upskill this team. We had a focus on security, application performance, cost management, and DevSecOps. And when we started this journey, we had zero cloud experience, and the team took self-training on GCP and Kubernetes in a span of 2 months. And all of us took in Kubernetes certification, ECK and GKE, as well as GCP certifications, which actually helped in the fast execution of this project. Here are our upcoming enhancements. We have a use case where we provide recommendations for similar support cases for our support engineers of Cisco. The similarity is based on text embeddings, and we use an open source KNN plugin along with Elasticsearch. And this is also hosted in GCP. It's just went live. We are working on learn to rank advanced intent detection and slot filling for both the content as well as the query. We are working on query similarity using embeddings, AI-based summarizations, and Istio-related changes. Overall, I would like to call out that when you combine the power of Elasticsearch and the power of what GCP can offer, it is very easy to build a very stable and highly cost-efficient enterprise search platform. And if you combine the power of AI in search, that makes it a very delightful customer experience. Thank you.